Okay, so I'm going to talk about multiplicative representations of integers. So I'm doing something I don't usually do or even like to do. In fact, I generally object to doing, which is talking about what I will call an old discovery. I say an old discovery as opposed to an old theorem, because you can discover something, even something that's true, but of course you're never quite convinced, or you're not supposed to, or others might not be convinced unless there's a proof. So there's a paper I wrote a very long time ago, and about multiplicative representations of integers. And I stated a theorem and I gave a proof. And every now and then I would look at this paper, and clearly it's a true statement, but I couldn't understand my proof. I mean, either it was wrong or I was just getting stupid and I couldn't understand the proof. So finally I had to be at a meeting in India back at the beginning of this year to give a series of talks, and I decided one lecture would be on this theorem because it would force me to figure out my proof or come up with a new proof or decide that the proof was hopelessly incorrect. So I think that the true answer is that the theorem is correct and my current proof is okay. And I just don't know whether what I wrote down, 20 plus years ago. So it's the following multiplicative version of a problem that has been mentioned in the seminar many times. So there is the so-called Erdős-Turan conjecture. Now, when I grew up, what I'm about to call the Erdős-Turan conjecture is what I always called the Erdős-Turan conjecture. They made several conjectures. They made one conjecture about harmonic series. If a harmonic series does something, then you have arithmetic progressions. And people always talk now about that as the Erdős-Turan conjecture. But for me, the real Erdős-Turan conjecture is the following. So let A be a set of non-negative integers. And as usual, A plus A, or 2A, is just the set of all sums of two elements of A. And we have a representation function. So R sub A of n is the number of pairs AA prime, where A plus A prime equals n. So it's the number of ways you can write n as a sum of two elements of the set. And the conjecture is that if Ra of n is at least 1 for n sufficiently large, then this function, the representation function, is unbounded. So this is the conjecture. So if every large enough number has at least one representation, then there are numbers with arbitrarily many representations. So an equivalent way to state this is that if the lim inf of Ra of n is at least 1, then the lim sup of Ra of n is infinite. And you can extend this obviously to h-fold sum sets. But since you can't prove it even for two summands, it's not really necessary. So this is the additive problem. And of course, there is the multiplicative version. So the multiplicative version would say the following. Suppose A is a set of positive integers, and we let A squared, or A times A, be the set of all products of two elements from the set. And suppose, let me use B for this, cool, because I used A in the additive case. And let's say that you have a representation function G sub B of n, which is the number of pairs AA prime. Sorry. I guess I should be using B's. B and B prime, such that BB prime equals n. And again, you can ask if every number or every sufficiently large number has at least one representation as the product of two elements of B, is the representation function unbounded? So that's actually not a conjecture, that's a theorem of Erdős. From 1964. So we have this set B of positive integers. And if every number has at least, every large number has at least one representation. So if the lim_inf of this representation function is at least one, then the representation function is unbounded. So in this case, the multiplicative version is not necessarily easy, but at least it's solved. And Erdős's proof used graph theory. And then a number of years later, there's a second proof due to Nathanson and Riddle. In 1985, that uses Ramses' theorem, Ramsey theory. And in fact, I'll show, in fact, how you, I'll give essentially the Nathanson and Riddle proof, though, without doing any serious lifting. You can extend it to H-fold products instead of just two-fold products. So this is the multiplicative version of the Erdős-Turan conjecture, and it's true. Okay. Now, often in additive number theory, instead of considering the H-fold sum set, we often take H different sets of integers and consider the sum of these H different sets. And similarly, in the multiplicative case, instead of looking at the H-fold product of a set of positive integers, you can take H different sets, B1, B2 up to B sub H, and take the product set. So this is just all numbers you can write in the form B1, B2 up to B sub H, where B sub I is in the set capital B sub I, for I going from 1 up to H. And one can define a representation function in this case. So suppose we let script B be this H tuple of sets of positive integers, and we can define a representation function G sub B of n, which is the number of ways you can write n in this form, B1, B2 up to B sub H, where the ith term Bi is in the ith set B sub I. So we, instead of looking at the representation function for a single set, we're looking at the representation function for a multiplicative system of sets. And again, one can ask, does the Erdős theorem extend to this case? If every number from some point on has at least one representation, is the representation function itself unbounded? And the answer is no. The analog of Erdős's theorem fails for multiplicative systems, and it's easy to put together counterexamples. For example, suppose I let this capital P be the set of primes, and I partition this set into, let's see, so this is a partition into H pairwise disjoint sets, and let B1 be all positive integers such that n is a product of primes in the set P1. And in fact, of course, you do that for each one of these H sets. So B sub I is the set of all integers which are products of primes in the set P sub I. So of course, 1 is in BI for all I. And the fundamental theorem of arithmetic is equivalent to saying that for this system, G sub P of n equals 1 for all n. So every integer has a representation, but in fact, the representation is unique. So the immediate analog of Erdős's theorem fails. So in this case, we have the lim inf, G sub B of n equals 1. And also the lim sup, this is not an implication, this is just a fact. The lim sup of G sub B of n is also equal to 1. Okay, any questions about that? That's interesting. But the remarkable fact is that in fact, the analog of Erdős's theorem doesn't really fail. Okay? It's just, it has to be looked at a little bit more carefully. And the following theorem is true. So you have this multiplicative system. That means this H tuple of sets of positive integers. GB of n is the representation function. The number of ways you can write n is a product of H factors, one from each of these sets. So this is the theorem. We know that if every number has one representation, that doesn't imply there have to be more. But if every number, at least from some point on, has at least two representations, then the lim sup is infinite. Okay. So that's the old result, if you like. And we can be a little bit more precise. So for H greater than or equal to 2, let M of H be the set of all pairs of integers S and T such that there exists a multiplicative system, this ordered pair, ordered H tuple of sets of positive integers, such that lim inf of GB of n is S, and lim sup n goes to infinity, G sub B of n is T. So this set M of H is all possible pairs S and T, where the lim inf is S and the lim sup is T. And what is M of H? So I will tell you, M of H consists of the following pairs. It's all pairs 1 comma T, where T is a positive integer or infinity, together with all pairs S comma infinity, where S is 2, 3, any integer from 2 up to H. Okay. So these are all the possibilities for this multiplicative system. So if the lim inf is 1, the lim sup can be any number from 1 to infinity. But if the lim inf is at least 2, the lim sup must be infinity. Okay. All right. And half of this theorem is easy to prove. So the easy half is that M of H contains all this stuff, right? So for every pair 1T, there's a multiplicative system. And for S infinity, there's a multiplicative system. So that's the easy part. And I mean, I'll show you it's easy because I'm going to do it right now. And it's just some simple constructions. So suppose B B1 up to BH is our multiplicative system. So by and now when I say multiplicative system, I mean every number from some point on has a representation as the sum as a product of elements from B1 up to B sub H. Oops, excuse me 1 second. I see something flashing on my computer, which means if I don't plug in the cord, the battery is going to die. Let's just take a second. Okay, save the day. So, so let's make a quick observation. Suppose the number n is a product of H positive integers. If n equal P is a prime, there are at most H ways to do that. You either have a bunch of ones, a P, and then some more ones. So GB of any prime is at most H. So in general, so always the lim inf of G sub B of n is between 1 and H, right? So I mean, there are infinitely many numbers that have at most H representations, so the lim_inf cannot be bigger than H. So in this set M of H of pairs S and T, we know that S is between 1 and H. That's all we have to look for. Let T be a positive integer. So the little examples I'm writing down are really very simple. So, but just for completeness, I really need to do it. Suppose I let B1 be the set of all positive integers, and B2 be the set of powers of 2, where k is between 0 and t minus 1, and B sub I is just the number 1 for whatever other sets we need, I going from 3 up to H. So the number of representations of any odd number is 1, because you have an odd number. This has to be 1, odd number times 1 times 1 times 1. So S, which is the lim_inf of this representation function, is 1. And what's the largest number of representations that's possible? If you write n as, 2 to the Lm, you can write this as 2 to, let's say L is bigger than T, 2 to the L minus K times 2 to the K times a lot of 1s, where K can go from 0 to T minus 1. And so the lim sup of G sub B of n is T. That is, for any positive integer T, I just wrote a simple example of a multiplicative system where the lim_inf is 1 and the lim sup is T. So that shows that this ordered pair 1T is an M of H for all positive integers T. And if instead of, if I just change this slightly, if I let B1 equal to n, B2 be the set of all non-negative, all powers of 2, and all the other sets equal to just 1, then in this case, S, which is the lim_inf, is 1, and T, which is the lim sup, is infinity. Just take a large power of T, and you can have as many representations as you like. So that says that 1T for all T, either a positive integer or infinity, is in this set M of H. Okay.
Mel, could you repeat the definition of M of H?
Yes. So, oops, let me get this out of the way. So I'm looking at these multiplicative systems. This is an H tuple of sets of positive integers. I let the number of representations of n as a product of H integers, 1 from each of those sets. That's this representation function. And actually, and I call it a multiplicative system if from some point on, every number has at least 1 representation. And I'm interested in, if I look at all multiplicative systems with H sets, what is the lim_inf and what is the lim sup of the representation function? So the Erdős-Tarán conjecture was, in the additive case, if the lim_inf is 1, the lim sup is infinity. And Erdős proved In the multiplicative case, if instead of taking a multiplicative system, you just take one set B and look at look at representations as a product of H elements from this one fixed set B, if the lim_inf is 1, the lim_sup is infinity. But for multiplicative systems, that's not true. And I gave an example of a multiplicative system where the lim_inf, where every number had a unique representation. So the lim_inf and the lim_sup were 1. I let M of H be all possible pairs ST, where for some multiplicative system, the lim_inf is S and the lim_sup is T. And the theorem, one part of the theorem is that, so you can have S and T both equal to 1. And the half of the theorem, the more important part, says that if the lim_inf is at least 2, so if in your multiplicative system, if every integer from some point on has at least 2 representations, then the representation function has to be unbounded. But in fact, I made a statement a little bit more precise. I said exactly what are all possible pairs ST in this set. And if S is 1, that is, if infinitely many numbers have unique representations, then there's systems where T can be any integer or infinity. And I just constructed some examples of them. But if S is 2 or greater, then the lim_sup has to be infinity. And I want to show that, and I showed that S, the lim_inf, cannot be any bigger than H. So if S is not 1, it's an integer between 2 and H. And for every such system where S is between 2 and H, the lim_sup of the representation function is infinite. That is, the number of representations is unbounded. So I want to construct an example of something like this. And I guess it's actually pretty easy. So for any S between 2 and H, let B1 up to BH be the H sets in a multiplicative system where B1 is all the positive integers, B sub I is the primes and 1 for I going from 2 up to S, and B sub I is just 1 for I going from S up to H, S plus 1 up to H. So if you think about this for not much more than a second, I guess, if you take a prime P, G sub the number of representations of P is what? Well, you can have some 1s, a P, and then the rest 1s. And where can this P be? It can be in any one of the first S places. So G sub P, so the number of representations of a prime is equal to S. And every number will have at least S representations. So the lim_inf is equal to S. But I claim that the lim_sup, G sub P of B, is infinite. Well, why is that? Well, here's a simple way to see it. Suppose N is a product of, I don't know, capital N primes. So we can write N as a product as N over Pi times Pi times a lot of 1s. This is in the set B1. This is in the set B2. The rest are just ones. But I can pick this prime pi in capital N ways. So this number n has capital N representations for any n. So there are infinitely many numbers that have n, at least n representations. So the limb soup is infinite. Yeah. I'm not sure if I explained it clearly enough, but this part is easy. So what that says is that in the statement of my theorem, all possible pairs S and T, well, each of these is possible. So M of H contains each of these. So what I have to show is the opposite inclusion. I have to show that M of H equals this. Now, what else can there be other than these numbers? If S is 1, T can be anything. So the only case is when S is 2. And in order for this to be an equality, you have to show that if S is 2, T is infinite. So that's the hard part of the thing. Okay. And so must show that if G sub B of n is at least 2 for n sufficiently large, then lim sub G sub B of n is infinite. Okay. All right, well, I said that Erdős used graph theory in his proof of the multiplicative basis result, and Nathanson and Rodel gave a different proof using Ramses' theorem, and it's Ramses' theorem or some iterated form of it that I'm going to use here. So let me just remind you, what is Ramses' theorem? So there's a finite version and an infinite version, and this is the infinite case. So this is a theorem that says something that happens for every k. So we have X, some infinite set. Countably infinite, I don't have to worry about anything. And square brackets xk, this is all k element subsets of X. So that's all subsets of X that have exactly k elements. And X less than omega is all finite subsets of X. So let me remind you of what is the infinite pigeonhole principle. So X is an infinite set. The infinite pigeonhole principle says that if X is a union of H subsets, then at least one set X sub I is also infinite. Okay. So I probably don't have to work too hard to sell you that result. Let me state it in a slightly different way. In a slightly different way, it says the following. If the set of all one element subsets, actually, what I wrote is good, but just to be consistent with tradition in a sense, let's say that we've partitioned X into H sets C1 up to C sub H, or just to be consistent with my own notation, C0 up to, I mean, it doesn't matter. Finite number of sets. So if you take an infinite set and you partition it into a finite number of pieces, into a finite number of subsets, then at least one of the subsets is infinite. Or an equivalent way to state that is, this is the set of all one element subsets of X. And if you partition this into a finite number of pieces, then there exists a set X1 contained in X, such that all of the one element subsets of X1 are contained in Ci for some I. Infinite. So this is just a silly way, if you like, to rewrite the usual formulation of the infinite pigeonhole principle, but it says the same thing. If you look at all the one element subsets of the set, that means all singletons, and you write it as a union of H plus one subsets, not necessarily disjoint. I mean, that's irrelevant here. But there's some infinite subset of X, all of whose one element sets are contained in one of these guys. Or, okay. And Ramses' theorem takes the infinite pigeonhole principle and generalizes it a bit. So Ramses' theorem says that for every k at least 2, if you take the k element subsets of an infinite set X and you write it as a union of a finite number of subsets, then there exists an infinite subset X sub k of X, such that all of the k element subsets of xk are contained in Ci for some I in one of these sets. So people like to use the chromatic language. So these are the k element subsets, and you color every one of them with one of H plus one colors, a finite number of colors. Then there's always an infinite subset of X, all whose k element subsets are monochromatic. They all have the same color. Okay. And yeah, okay. Now, what I need is a sort of an iterated Ramses theorem. I mean, all of this, everything I'm saying is infinitely well known. The iterated Ramses theorem would say the following. So again, X is some infinite set. And for every k, let the k element subsets of X be written as a union of, let's say, R sub k subsets. So I'm not doing this just for a single k, but for all k. And the number of sets in this partition can vary with k. There exists an infinite decreasing.
Sorry, just checking. The superscripts on these C's, they just indicate that these are the set C associated with the k-tuples of X, right? They don't mean take k-tuples of C's.
Oh, you're right, exactly. So the superscript k means that these are sets of k-tuples of X. And yes, so I'm partitioning this set of all k tuples of x into a finite number of pieces. And there's an infinite decreasing sequence of sets. X is x0 contains x1 contains x2 and so on forever. And an infinite sequence epsilon sub k with every epsilon k, some integer between 0 and r sub k, such that the k element subsets of the set x sub k, infinite decreasing sequence of infinite sets, the k element subsets of x sub k all have the same color, are contained in C epsilon sub k. So, for example, if I take xk, the k element subsets all have the same color. The 2 element subsets all have the same color. The 3 element subsets all have the same color up to the k element subsets because of this inclusion.
No assumption is being made about the intersection of all of them, right? That could be empty for all you know.
Correct. Yeah, because I'm always going to, yes. All I know is it's, yes, exactly.
They're infinite at each finite stage, yeah.
Yes, exactly. Okay. So in order to prove Erdős's theorem for multiplicative bases, where I take all the sets in this multiplicative system to be the same, I need this iterated Ramses theorem. But to prove my theorem, I need a iterated Ramses theorem. Whose proof I realized earlier today is completely trivial also. And the iterated Ramses theorem says the following. So we have X is some infinite set. And for every non-negative integer k, we have the k element subsets of X. And it's not just that we partition this into some finite number, rk plus 1 is the notation here, of subsets, but in fact, I have a whole series of such partitions. Okay, so, and I don't have to restrict the number. Let's say though, so for example, if k is 2, I partition the 2 element subsets into finite number of pieces, and then I also partition the 2 element subsets in another way in a finite number of pieces, and maybe in a third way in a finite number of pieces, and so forth. So I have more than one partition of the k element subsets, but everything is still good. There exists an infinite decreasing sequence. X contains x1, contains x2, and so forth, of infinite sets. Such that for every k, if I take the k element subsets of x sub k, this is contained in one of these sets for each I. So it's contained in some ck epsilon k sub I comma I for all I going from 1 up to h. So I have like h different ways of partitioning the k element subsets. But I can always find an infinite set k such that each of the k element subsets of this infinite set is in one set in this partition. And the same statement is true for every one of those, that finite number of partitions. Okay. So this is my sort of doubly iterated Ramses theorem. And again, it's no big deal, but it's what's needed. Okay, now, how does this help me with my multiplicative system? So of course, there's an intermediate step, because in Ramses' theorem, I'm dealing with sets of integers, and it's easy to use Ramses' theorem in the following way, apply to sets. So this is a sort of a purely combinatorial theorem. So H is at least 2, X is some countably infinite set. Script A star is consists of H collections of things, and each A sub I, every one of these things, is a set of finite subsets of X. So I have this infinite set X. It has a lot of finite subsets. A1 is some collection of finite subsets. A2 is a collection of finite subsets. Up to A sub H is a collection of finite subsets. And for every finite set S in X, I want to let G, this is my representation function, A star is this H tuple of sets of finite sets. This is the number of ways you can write S as a union of H subsets where AI is in script AI for all I, and these sets are pairwise disjoint. Okay. Ooh, exciting. So the easy version says the following. If shut that off. If the number of representations of the set S is at least 2, for all but finitely many sets with n elements, then there is a set S with n elements such that G sub A star of S is at least n. All right, so let's see. Let me just repeat this again.
What's the inequality? At least what?
Oh, n, sorry.
And it's the same n? The same
Yeah.
n that you were just using?
It's the same n. So you have a countably infinite set X. We have an H tuple of sets of finite subsets of X. And for every set S, finite set S, I want to count the number of ways I can represent S as a union of H sets, one from each of these collections, which are also pairwise disjoint. And the theorem says that, let's say for every n, if every set with n elements, with maybe a finite number of exceptions, has at least two such representations, then there is a set with n elements that has n representations. And yes, n representations. And what that means is, if I look at all sets with size S, the representation function in terms of writing the set S as a union of pairwise disjoint subsets is unbounded. I just choose n as large as I like. Right? So this is the combinatorial result that is proved using, well, I mean, maybe there are other ways to do it, but it's proved using this doubly iterated Ramses theorem. And, okay, so let's make believe that this is true, and I have a proof. I claim then that I'm done. I proved the number theory theorem. So I want to prove that if I have H sets of positive integers, and every number from some point on at least can be written as a product, has a multiplicative representation. And in fact, every number from some point on has at least two multiplicative representations. Then the representation function is unbounded. So integers themselves are too complicated. Suppose I look at just square-free integers. So consider square-free or quadrat-free. For some reason, people used to like the German for this, integers. 1, 2, 3, 5, 6, and so forth. You factor a square-free integer, n. If you factor it as a product of H numbers, these numbers are all certainly square-free, and they're also obviously pairwise relatively prime. Of course, you can't have a prime occurring twice, so you have a square of a prime dividing n. And you have this way of going from, let's say you have the square-free numbers q, and the set of finite sets of primes. So you have a function from one to the other. Phi of a square-free number is just a set of primes that divide n. And you have an inverse function, phi inverse of a finite set, I don't know, t contained in the set of primes is just the product of all the primes. And you can see if n is a product of, if n is a square-free number that factors, the set of primes that divide n is the union of the primes that divide each of these individual factors. And these sets of primes are pairwise disjoint. So you have a kind of one-to-one correspondence between writing a square free number as a product of h integers, and writing a finite set of primes as the union of h pairwise disjoint sets. And this kind of dictionary, if you like, between square free numbers and the sets and finite sets of primes, if you take the statement that every integer from some point on has at least two representations in the multiplicative system, means every square free number from some point on has at least two representations, which means when you're looking at these finite sets, you have at least two representations of the finite set as a union of pairwise disjoint subsets. And the theorem that the number of ways to do that for sets is unbounded means that the representation function for the multiplicative system, restricted to square free numbers, is unbounded. So I'm not sure how clear that is, but that's how you prove the theorem. And I can say there's two references for this. So there's a paper I wrote in the Israel Journal of Math in 1987, where I stated and maybe proved the theorem. And but I posted on Archive a few days ago a version of the paper. I mean, it should be the same proof, except I just couldn't understand my original proof. And I also, in my original proof, didn't have this doubly iterated Ramses theorem, which I think I need. Or maybe I understood it, but I didn't write it down at the time. But in any case, there is a preprint on Archive, which I believe is completely kosher and is okay. Anyway, that's the whole story, and I thank you all.
Thank you.
Thank you.
Let's see. I would love to unpin this if I can figure out how to do it.
Many thanks.
Add pin, unpin. Huh. Replace pin. So above my pay grade.
Should be a switch to gallery view somewhere. I think that's what you're looking for.
Yep. But I was just trying to get rid of this. Well, remove pin. There we go. Okay. No, I muted myself. Anyway. Okay. So earlier today, I sent out an email. We have our last talk of the semester is next Thursday, which is Biswas, who's here, who's going to talk about minimal systems of some sort. And yeah. So why can't I unpin this? Stop video.
You can stop the recording also if you wanted. That might